If not, let's get to the main show and invite Dr. Katie Brody and Jesse on up to the stage. Thank you very much.
All right. Hey everyone. Thanks for coming to hear us talk about some of our research. The research we're going to be talking about today sort of sits squarely in ERDIC's force projection mission area, and so coming up with new ways to provide situational awareness data during entry operations through the surf zone. And so the title of our talk today is Rapid Beach, Surf Zone, and Littoral Reconnaissance, and we're going to talk to you about some of the technologies that we're developing to do that. So why do we need these technologies? What's the problem? There's lots of historical databases that have water depth maps. There's charts that you can buy that are available. But the problem really is that these data sets become out of date really quickly. You know, as soon as we have a change in the weather patterns, the waves start coming from a different direction, we have a storm moving by, everything changes on the beach. The beach erodes, it might grow, the sandbars move offshore, they might move onshore, it gets shallower and deeper. So it's really an area that changes very quickly. And so we have to have a way to rapidly update basically what the state of the littoral zone is. What does our beach topography look like? What does our surf zone bathymetry look like? Because if we're trying to do an entry operation where we need to cross this region, we want to know, are our boats going to run aground? What are the approach slopes on the beach? Information like that.
We've got, you can see in the left-hand panel also some of the examples of traditional ways to get bathymetry and topography that don't work very well in that environment where the waves are breaking, lots of bubbles, lots of turbidity.
So one of the solutions that we've been working on is instead of trying to see through the water like your traditional LiDAR might do, or your sonic altimeters where you might need to be on a boat actually in the surf zone, which is pretty dangerous, we're actually taking images of the waves as they travel across the surf zone. And so you can see sort of in this image on your right here, you can see the waves bending or refracting around the different water depths. And so we can basically exploit how those waves bend and refract through shallow water and figure out what water depth they must be in. So specifically, we're measuring the speed that they're moving and where they're breaking in the shallow water, and we use that information to infer what the water depth is. So that allows us to map the water depths close to shore. So we've really developed a suite of different sensors to tackle this problem, and because one sensor modality doesn't really work perfectly all the time, and so there's lots of different ways that you can approach this. And so I'm going to be talking about some of our image-based products that we've developed today using RGB or IR imagery, and Jesse's going to talk a little bit about some of the radar-derived products. And so we've sort of split this image up into sort of two sides for you. And we have a couple different ConOps associated with each one of those sensor modalities, and some of them work well from offshore looking onshore, some of them work better onshore looking offshore, some work at night, some work during the day, more inclement weather or better weather. And so there's a lot of different tools that we're working on, really trying to identify the best applications of all of them.
But all of them are exploiting, as Kate said earlier, the idea of looking at the wave behavior, their speed and how they bend around to then infer what the depths are and hazards are. That is taking a bit for it to queue up.
Oh, there we go. Third time's the charm. So I'll go ahead and get us started with some of the image-based solutions. There's three main ConOps that we've been focusing on. So we're calling these littoral imaging systems, or LIS, and we have a hover concept, mobile concept, and then a more stationary tower tethered concept. And each of them are going to support a little bit different mission area. The hover system is really going to give you quick answers in about a kilometer region along the coastline. The mobile application would allow you to survey longer stretches of coastline, about 10 kilometers in a half hour from a little bit higher altitude. And this tethered option or a tower-based option would be something that you might use more in a JLOTS type operation where you're going to be maintaining a site on the beach for multiple days or weeks at a time, and you want to understand how your topography might be evolving during that time period. So I'm going to talk in a little bit more detail about the hover application because this technology is at the highest TRL level. So for the hover application, what you do, the concept is you would basically take off with a commercial off-the-shelf system like a little 3DR Solo that just has a regular camera on it. You'd hover in place for about 10 minutes and take a movie of the waves coming towards the shoreline, and then you'd spend the next 5 minutes and fly up and down the beach and then land. And then from that, your flight up and down the beach, you can use basically standard photogrammetry structure from motion approaches to give you the beach topography. And then we have these wave kinematics algorithms that we run on the 10-minute hover movie to calculate the water depths. And so this image in the middle is just an example. The colors are showing you the elevation along the shoreline, and then the water depth contours are the bathymetry product that we can produce. One of the other things that these image processing techniques can show you is where waves are breaking in the surf zone. And so if you're in a boat that can't handle breaking waves very well, it would show you the areas to sort of avoid. You might want to pick deeper regions to come ashore. And then we can also get initial estimates of longshore currents or identification of where rip currents might be. See if this is going to play. So this is just an example of what the merge data product looks like. Once again, the bathymetry contours are shown in the surf zone portion, and then the colored imagery is a 3D point cloud generated from the structure from motion, and then we can merge those together so that we get seamless data on the beach topography and the water depths close to shore. And one of the things we like to do is take oblique imagery of the topography as well as looking straight down on the topography, and that allows us to identify sides of buildings and pick out features like a tower and other obstructions a little bit better, and make sure we get really good data on the face of that dune, because if that's something you might have to cross, you really want to know what the slope is and what types of obstructions you might encounter there. And lastly, the two other modalities I talked a little bit about, our mobile application actually combines multiple cameras to generate a really wide field of view. And so what that enables us to do is as we fly along the coastline with this really wide field of view, we can build up that dwell. And so it allows us to actually collect that 5 to 10 minute dwell data of the surf zone as we're moving along the coastline. And so that's at a little bit lower TRL level right now, but we're still working on exploiting those data. And then the final modality is sort of more of the tether or tower. That would be if you are going to be stationed on the beach for a longer period of time and you want hourly updates of what the surf zone conditions are. And you can do some processing to, if the water is clear, you might be able to look through the water, basically look through the waves by doing some analysis on that long dwell imagery to find mines. Or it will also sort of give you a map of where the sandbars are, where they're changing, what your inundation region is looking like. So if you want to stage your equipment, you want to make sure you're staging it above where you might have inundation from the water. And so as your topography is changing, you could use that to flag areas or buildings that might be more at risk.
The SWIFT system is a low-powered radar. You can see an example of it in the lower left-hand side. And the idea on that was it's a lower fidelity than the sensors and approaches that Kate described earlier. But the idea behind it is it's a very inexpensive and mobile system that works in nighttime and other really adverse conditions. And you can see an example of the raw data in that upper left-hand movie panel. Those white blobs are waves moving across the surf zone. So the idea idea is that it could be easily mobilized on a lark or other AAV that's on the beach, or just stood up statically with the two-person team, collect for 6 to 10 minutes, and then provide products in about 5 to 6 minutes after that point. And one of those products is what the depths are across the surf zone. So the colored panel in the middle there, that's looking from map view, and the warmer colors represent shallower waters. And it spans about a 200 meter in the alongshore stretch. So the gray, or excuse me, the brown area is the beach. In fact, this was from Camp Pendleton at a recent demonstration exercise this past spring. And the cooler colors represent deeper waters as you cross the surf zone. The upper panel is just a depth profile that the user can click at the beach, then offshore as a potential route that they might take, and you can see what the depths are in profile view in that upper panel. The second area, and Kate introduced this earlier about hazards that you can look for from these different sensors. This is showing on the upper left-hand panel an example of a quick product that shows you where the waves are most intensely breaking and where they are not. Again, as a first cut at where you might want to consider crossing the surf zone. It's also very sensitive to mines. The imagery that Kate showed earlier, you can see through the water. This is where the mines are causing a disturbance of the water surface right in the very shallow swash area. And the lower right panel is, again, an example of how we can use these sensors to see rip currents or other hazards in the surf zone. We'll talk together.
Yep, and so finally, all of these products that we've introduced here work on their own as standalone products that give you an answer about the topography and the bathymetry, but one of the other things we're working on is integrating it with numerical models to actually provide a tactical forecast. And so we're doing that two ways. One is through data assimilation, where we're actually assimilating some of the observations like the wave speeds and the current magnitudes into the numerical models and allowing them to help us solve for the bathymetry. That gives a higher fidelity answer. But then what you can also do is run that model in forecast mode, which then gives you a tactical forecast of the next few days or something like that, and what the conditions are going to be. And so we're working closely with our numerical modelers to make sure that all this data is easily ingestible and also has an uncertainty estimate associated with it. So not only are you providing a map of water depths and topography, but you're also saying how good you think that estimate is. And so then that can inform your risk assessments of where you want to go in.
And I think that, just to summarize what Kate said too, the suite of sensors we use, I think, can operate in a lot of different environments, a lot of different conditions from different platforms, but we can't forecast, and we need the coupling with the model to give a forecast of what conditions can be like. Any questions?
I think that's all we had for you today. Right, so the question is on the turnaround time for the mobile data. And that's probably our slowest turnaround time right now. It obviously depends on sort of the region that you're trying to survey. And a lot of it is driven by the computing power to process the imagery for the topography. The bathymetry side is actually really quick. We can do the bathymetry over that region in an hour. Right now, the processing of the imagery to get the topography takes a lot longer. So that right now we're looking at multiple days. If you can ship it up to like a high performance computing system or something like that, it can be reduced significantly. And we're working on ways right now to improve the processing time there and figure out what fidelity answer we really need, and where you can make adjustments in the algorithm to make it faster.
Some of the other sensors, though, do provide a faster turnaround. You lose fidelity in the answers, but the little Swift system, we can get answers in about 5 minutes. So it's
Yep, so the question is about collaboration with other government agencies. So we've definitely been working closely with some of the NOAA folks and also the Naval Research Lab folks to sort of work on these technologies together. So I think the stealthiness was referring to your radar system.
Yeah, and the idea is it's very low power. It's less than about a fifth of the transmit power on your phone, and it's a chirping radar, so it's more difficult to detect.
Yeah, the bottom line is if you don't want to take the necessary
Correct. And that's in part, we also want to reduce the dwell time as well. So, we're looking at those 10 to 15 minute kinds of dwell times and not hours to do that.
All right, I think our 15 minutes is up.
Thank you.
Thank you so much for listening to us today.
The next presentation will start at 12 o'clock.